Thank you very much, Serge, for this very nice introduction. It's a pleasure to be here. I'm happy to take you on a journey about where we talk about Bluetooth and pitfalls of wireless protocols. Giving a keynote is always a challenging endeavor. And as a keynote speaker, it is my job to, on one hand, entertain you, but on the other hand, talk about some of the key issues that I may observe that need fixing in this area. And in the last year or so, we focused, or in my group, we started focusing on Bluetooth and several Bluetooth protocols. And we have found quite a bit of interesting issues that happened along the way. But as a keynote speaker, it is also my job not to just talk about my work, but also to enable you to talk about other people's work and to give you a platform that then allows you to exchange information and start a discussion and come up with your own research topics. And I think in my personal opinion, a good keynote is a keynote where after the keynote, you can actually meet at the coffee break, discuss, exchange, and have a couple of topics to start discussions with random people. So this gives me the opportunity to highlight some of these parts. If you do have questions throughout, I think Serge just added the Zulip chat link. You can also use the chat. I'm happy to take questions throughout, but also at the end, whatever you feel more comfortable with. Now, I know keynotes are usually rather long, so let me just start right away with the key takeaway. And we have to start an emergency meeting here about the issues that Bluetooth is facing. And the key takeaway, if you only remember one part of this talk, is that it's complexity XOR security. If you have high complexity, you will have security issues. And this is the key problem that Bluetooth is facing nowadays. And it can be broken into two parts. First off, Bluetooth is way too complex. On one hand, the protocol itself is extremely complex, and the implementation is extremely complex. The attacks that we are seeing nowadays attack all the layers of Bluetooth across all the different layers of the stack. There's on one hand standard compliant attacks against the protocol itself, but there's also broad implementation bugs both on the controller and on the actual host. And this has been an issue for several years already. But with the increasing ubiquitousness of Bluetooth devices, it is becoming ever more pressing that these issues are actually fixed and recovered. So the key takeaway from this talk is we need to reduce complexity to increase actual security benefits. Right? So Bluetooth as a protocol itself is too complex, resulting in protocol issues and implementation issues. I will now structure the talk into three different parts. We first will discuss different kind of protocol issues. So what is happening at the protocol layer? And I think this will likely be most interesting for the CANS folk. And then we'll talk about different kinds of implementation issues. What kind of actual attacks are we seeing? What kind of actual bugs are we seeing? And how can we work through those? And then, to make sure that not all hope is lost, and to end on a positive note, we'll discuss different forms of mitigations and how to make Bluetooth more secure and increase the utility of this protocol. So join me on this journey across protocol attacks, implementation attacks, and then ways to move forward and increase the actual security. In the end, Bluetooth is not just, I'm sure everybody of you has heard of Bluetooth, be it just that you need to disable it when you take off in a plane, or when you used to take off in a plane in 2019, right? But in the end, Bluetooth is not just one single protocol. It's a complex suite of protocols, and it's basically a tale of two different protocols that are existing next to each other. On one hand, there's Bluetooth Classic that you may know from your headsets, from your input devices, from your car stereo, from your printer, and kind of all other devices. These are somewhat high throughput devices and require reasonably low power. More recently, there's Bluetooth Low Energy that came up, which is low throughput and very low power. So this is often used for tracking beacons, keychains, localization, but also things like smartwatches, heart rate monitors, and so on. These devices are designed for very low power, and Bluetooth Low Energy satisfies this. It's almost as if the Bluetooth, so the only thing that the two protocols share is the name. Bluetooth Low Energy is a very different stack compared to Bluetooth Classic. And it's almost as if the Bluetooth consortium thought about adding a second protocol that when Zigbee got too popular. But the key takeaway here is there's Bluetooth and Bluetooth Low Energy. Both are two kind of protocol suites. And that there's something in between. There's all these devices that we carry around in our pockets or in our backpacks as laptops and phones that actually speak both protocols, both Bluetooth Low Energy and Bluetooth Classic. And we'll see that this duality of the two protocol stacks will offer a nice set of attacks or attack vectors. So the core of this talk will focus about security aspects of Bluetooth. But I would also like to mention some recent work that we did under the umbrella of the COVID-19 issues with decentralized privacy-preserving proximity tracing, where phones exchange random Bluetooth IDs, COVID-19 positive. People can upload these IDs, and then there's a local check on the individual phones if exposure is beyond a certain threshold. And this is pretty much how I spent all summer, ignoring the main quest of Bluetooth security to do this high XP side quest that allowed me to gain much more than I ever wanted to know about Bluetooth proximity and underlying Bluetooth protocols as part of measuring all these effects also with a large set of people. That was very interesting. But enough side quests. Let's head out for the main quest and see what we can do, and start with the key aspect here: protocol complexity versus protocol compliant attacks. The Bluetooth specification is incredibly complex, incredibly convoluted, and has grown over many years. The Bluetooth consortium, or the Bluetooth special interest group, is a consortium of many different companies that all bring in their ideas. And as with many consortia, this ends up being a very complicated, multi-layered system. And for Bluetooth Classic, this is there's all these different layers in here that go from Bluetooth radio over baseband to link layer. This is what we already know from other kind of networking systems. And then on top of the host controller interface, you have a flurry of additional protocol suites. So you've got medical profiles, you've got communication profiles, you've got uncompressed audio profiles, and a lot of other different alternatives and opportunities. And you may wonder why a communication protocol actually needs to implement, as an example, format to exchange business cards encoded in XML over an OBEX remote procedure call that then sends up this data through a serial line on top of a Bluetooth connection, right? So this business card exchange protocol in XML that triggers remote procedure calls on the other end is part of the Bluetooth standard. This is incredibly complex and likely not needed. Overall, the Bluetooth specification is 3,256 pages for version 5.2, and there's no reference implementation whatsoever. If you discover any bug in the spec, you will have billions of broken devices at your disposal. So there's a huge attack surface out there. And the spec is incredibly complex, and without the reference implementation, it's highly likely that there's gonna be vulnerabilities or additional vulnerabilities in there. Let's spend a little bit of time to talk about the Bluetooth security architecture. I don't want to give you a complete primer about how the Bluetooth protocol works. In the end, this is only a 1-hour keynote and not a one semester class. If you're interested, I'm happy to talk more, but I just want to give you the high-level points about the Bluetooth security architecture. The Bluetooth security depends on 2 steps. Step 1, devices pair once in a pairing phase to create a long-term key. And this pairing phase makes sure that the devices authenticate each other and that both devices in the end, after pairing, have a shared long-term secret. Based on this long-term secret, they may then create session keys and connect to initiate these secure sessions and then communicate on top of these secure sessions. Like, this is the basic underlying system, how it works. There's no central root of trust. The basic trust is created when the devices actually pair for the first time. So downsides of this Bluetooth security architecture is that Bluetooth has a legacy mode to enable backward compatibility. Now, if you have already a couple of million or 100 million devices sold, which are not necessarily updatable or hard to update, you need some form of backward compatibility. And legacy mode enables this form of backward compatibility. Also, Bluetooth has existed for a long while, so there's a lot of devices out there that will definitely no longer be updated. The protocol also specifies an "it just works" flavor of protocol connection. It just says, oh, everything will work out fine. We don't need security. Security is way too much overhead. So let's just try to communicate and see what happens. Also, with the addition of Bluetooth Low Energy, there's this idea that suddenly the two protocols that are two distinct protocol stacks may interact in very weird and unintended ways. And it's definitely something that we should look at. So keep these kind of features in mind as we walk through the different protocol attacks. And I will talk to you about 4 different protocol level attacks that are protocol compliant and that pretty much broke every single Bluetooth device that is out there in the field. Let's start with the knob, the key negotiation of Bluetooth attack. And as part of the key negotiation, when you're creating session keys based on the long-term keys, the two pairs, Alice and Bob, negotiate some form of entropy that is being used for the session key generation. As devices have different computational power, this negotiation would allow low-powered devices to specify a lower entropy because it would exceed what they have available. So Alice talks to Bob, asks for key entropy of 16 bytes. Bob says, oh, best I can do is 15 bytes. Alice says, this is fine, I accept. And after that, the key entropy is 15 bytes, and they will negotiate their session key and start communicating. And this is work by Daniele Antonioli, a postdoc in my group that he did before he joined the Hex Hive group. Now, by itself, this is fine. And if the key entropy exchange is protected, everything will work out. Unfortunately, the key entropy negotiation happens in clear text. Now, if you add malware as a man-in-the-middle attacker that can prohibit the relay of messages, malware will stop the key entropy of 16-byte request of Alice to transfer, but in the end replaces it with a key entropy of 1 byte. Bob returns and says the minimum entropy of 1 byte is accepted because that's the only thing Bob can do. Mallory forwards another message to Alice, says key entropy of 1 byte. Alice accepts as well. And we now have a session key with a 1 byte entropy, which allows Mallory to easily brute force the underlying session key between Alice and Bob by just injecting a couple of simple messages that override the key entropy. This allows Mallory, as a man in the middle, to learn the session key without actually knowing the long-term key as the two devices are connecting. So this can be pretty much summarized as 16 bytes of entropy. Oh, well, best I can do is 1 byte. This is all you have. And the protocol standard accepts this, this low level of entropy, even in the most secure form. That's the first attack. Let's move on to the next attack, also against secure pairing. This is the bias attack, Bluetooth impersonation attack, that was at Oakland this year, also by Daniele. In the end, under secure pairing, you want to make sure that both Alice, like if Alice connects to Bob, she wants to make sure that Bob knows the long-term key, but the other way around as well. And you want to have two-sided authentication of the two parties. So when Bob starts connecting to Alice, he initiates a secure pairing phase. Alice responds with a secure pairing phase. Both exchange random values. Bob creates a hash with the long-term key, the randomness that Alice sent, and his Bluetooth address. Alice returns a hash of the long-term key, the entropy that was sent from Bob, and the Alice's Bluetooth address, and both check that the challenge has actually been satisfied. So we have a two-sided authentication of the two. Everything works out well, and secure pairing then authenticates both Alice against Bob and Bob against Alice, and everything is as it should be. Now, unfortunately, there's something called legacy pairing, right? And this allows Mallory to establish a secure session with Alice as Bob without having access to the long-term key. So as part of the connection process, Alice downgrades from secure pairing to legacy pairing. So Mallory initiates with legacy pairing as B. Alice responds, sure, I'll do legacy pairing. Mallory sends 16 bytes of randomness. Alice happily computes the challenge, and Mallory simply ignores the challenge response, and they happily continue and agree on a session key. And in that case, Mallory was able to establish a session key with a secure session with Alice without actually being authenticated from Alice's side. So this was an Oakland paper earlier this year. But enough about Bluetooth itself. Let's look at Bluetooth Low Energy in addition to that, because Bluetooth Low Energy is also a very fun protocol. Again, here the same issue is that there was a part of the negotiation was in the clear, and man in the middle attacker can actually relay and create arbitrary messages. Now, for Bluetooth Low Energy, the protocol is a little bit different. There's the connection starts out in clear text and then in plain text, and then you can add additional encryption on top of it. So if Alice and Bob are communicating, they connect to each other. Alice requests an attribute from Bob. So Alice is the client and Bob is the server in this example. Bob returns and says, hey, this is insufficient encryption. I cannot send you this value because it's a very, very secret value, like the battery level that you're trying to read out. Both of them will agree to enable encryption and move to level 2. Alice will request the attribute again, and Bob will then reply with, hey, this is the super secure attribute that you asked about. Now, there's two issues with Bluetooth Low Energy reconnection attacks that we discovered. The first issue is a protocol issue. The second one is an implementation issue. Let's start with the protocol issue. So Alice and Mallory are communicating. They start at level 1 plain text. Alice requests an attribute from Bob, and Mallory simply returns a spoofed value without asking for level 2. Now, Alice will happily accept the spoofed value because the server is expected to throw the exception and then trigger the move to the encrypted value. So if the server or a malicious party simply responds, there's no encryption necessary and everything will happen in the clear text. The second attack level is more an implementation issue, and this was true on the devices that we tested. Again, the two parties communicate in clear text on level 1. Alice requests encryption. This would be the valid approach. Mallory obviously doesn't have access to the key. Says encryption fails. And instead of aborting the protocol, Alice will continue and simply request the attribute, which then allows Mallory to return the spoofed value and just say, hey, level 1 is fine. We don't need to move to level 2. And Alice then accepts the value. Right, so this is an implementation issue that is now in the process of being fixed. Again, the underlying issue here is that a lot of the negotiation happens in the clear text, and an attacker with network level access can actually inject malicious messages and then compromise the protocol as it happens. Let's move on to a different layer of the protocol stack and talk about the blur attack most recently, where we are blurring the lines between Bluetooth and Bluetooth Low Energy. A lot of the features in the Bluetooth protocol are to enable some form of usability to make it nicer for the different systems, for the different parties to exchange. And I've already told you that Bluetooth and Bluetooth Low Energy are two very different protocols. If you want to use both Bluetooth and Bluetooth Low Energy, you would have, without this feature, you would have to pair twice, once over Bluetooth and once over Bluetooth Low Energy to create two long-term keys. And this is why the Bluetooth standard defines cross-transport key derivation, which allows you to create, to pair once and create keys for both Bluetooth and Bluetooth Low Energy. So let's have a quick look at how this works. Alice and Bob's have paired over Bluetooth and trigger cross-transport key derivation, which then creates a Bluetooth Low Energy long-term key as well. Afterwards, they can connect both via Bluetooth and Bluetooth Low Energy, enabling them to actually play with both sides. Cross-transport key derivation simply takes the Bluetooth key and, based on a fixed set of processes, creates a long-term key for the other transport based on the first key that was generated. Now, the issue here is that due to the differences between the two protocols, the cross-transport key derivation approach allows an attacker to compromise long-term keys. Now we again have Alice and Mallory. Alice has already paired with Bob over Bluetooth, but due to different issues with Bluetooth Low Energy, Alice remains pairable through CTKD, cross-transport key derivation, on both transports. So Mallory can happily trigger pairing over Bluetooth Low Energy as Bob to create a new key, new long-term BLE key as Bob for Mallory. And then by forcing cross-transport key derivation, Alice will overwrite the original key that she had for Bob with the key that was just generated for Mallory. And Mallory has now replaced both the Bluetooth Low Energy long-term key and the Bluetooth long-term key, and Bob may no longer connect. Mallory can obviously do this on both ends and then inject herself into the session between Alice and Bob, thereby compromising any form of Bluetooth connection. Again, there's unintended interactions between the two protocols that were never analyzed in the security model. I've now given you a flurry across 4 different attacks against Bluetooth. This list is by no means complete. And as you see here, based on the CVEs, those were only attacks from the last year. So just in 1 year, we have these severe attacks against all the different layers of the Bluetooth protocol stack. And these attacks are all standard compliant, which means that pretty much every device out there is vulnerable to these attacks, as these are protocol specification-based attacks. As I said, there's a lot of attacks on Bluetooth that happened before this, and this is just a recent survey. I'm very certain that these are not the only attacks that exist. And if you are a PhD student or postdoc or other interested party, I'm sure there's many more additional attacks that you can find in these specifications. It's a tough read because it's quite extensive, this documentation, but I encourage you to actually go through all of these different parts, and it's a fun read, and you will find new issues fairly quickly. So this is a research area that is actively picking up and gaining momentum, especially as we are working on these different ends. So I encourage all of you to actually look into this. So that's what I wanted to tell you about the protocol compliant attacks. Let's move on to some form of implementation complexity attacks. Right? We've talked about the different layers that the Bluetooth protocol has. And all of these layers result in quite a massive code base that exists, both on the host itself, which is, for example, your phone or your desktop or your laptop that runs the Bluetooth daemon, but also on the actual controller, which is the Bluetooth radio chip, which runs a small little device and contains some additional state. Right, so the implementation attacks can target both. And I want to highlight 3 different projects here that I found extremely interesting, both from things that we are doing in my group, but also things that other groups have been doing. And I want to give a special shout out to the SEMO lab at TU Darmstadt, who's been working on this for a while and doing very interesting work. With Internal Blue, which is a Bluetooth binary patching and experimentation framework. And they are selling this and positioning it as some form of Bluetooth experimentation toolkit. But in the end, what they discovered is that Broadcom chips, which is I think the most common Bluetooth chip that exists, Broadcom chips have specific vendor specific commands that allows someone on the host to read and write on this embedded system to then, for example, extract the firmware or to modify individual parts in memory about the protocol state, about the connections, keys, and so on. So this can be used to patch additional functionality into the Bluetooth controller and to modify the controller alongside. They've had interesting work on firmware extraction, firmware modification, and breaking this kind of hard box of obscurity that these embedded systems have. And by having access to the firmware for the first time from these devices, they managed to analyze the underlying firmware and discover a large amount of bugs. So this was very interesting work that then spawned a lot of ongoing additional work on top of it, because we now had access to the internal state of the controller, enabling us to modify these different parts. Another work from the same group that I want to point out that was this year at Woot is toothpicker, where they followed a similar idea, but not targeting the Bluetooth controller, but actually targeting the Bluetooth daemon on iPhones. They rooted an iPhone, got developer access to it, and then started fuzzing the Bluetooth daemon from both ends, from the host end and from the driver's end, thereby discovering a lot of vendor Apple specific protocols and protocol issues. So as it turns out, Apple apparently thought that Bluetooth itself was not complex enough. So they piggybacked additional protocols on top of Bluetooth that implement additional Apple-specific or Apple internal functionality that is obviously not documented externally or publicly documented, and resulted in several vulnerabilities. So check it out. The Woot paper is available, and it was a really fun paper to read or watch the talk. Another point I want to mention is Bluetooth fuzzing, like following up on the previous work. It's an interesting opportunity to start testing all of these devices. In the introduction, Serge actually mentioned that my group is working on different kind of software testing, and this is an amazing opportunity for us to pinpoint and target all of these different parts. So a Bluetooth system consists of a host, which has a kernel driver, a user space daemon, and all the complex state that enables applications to start Bluetooth connections, search for devices, and interact with these devices. But there's also the Bluetooth controller, which is an embedded system, a system on a chip that runs a real-time operating system and has some state about the individual connections and all the different parts on top of it. And then you're obviously accessing the radio chip to send data back and forth and to do fun things. So by itself, this is a very complex system that would be very hard to analyze. But what we have done in earlier work where we looked at the USB stack is to separate these components or separate complex components and then to analyze them step by step. This is one aspect that we are looking at, right? So we can, for example, start fuzzing from the radio end by virtualizing the Bluetooth controller and mapping it into a virtual device, and then accessing this with these systems and moving data back and forth. right? By providing information from the host end, fake information, we can trigger the Bluetooth controller into interesting states and see how it reacts to certain radio messages that come over the air. We can also look at the other end by starting and seeding fuzz inputs from the HCI host controller side and into the controller, and by providing an abstraction of the radio chip, we can trigger interesting behavior on the controller from the other end, right? So it depends if the attacker is sitting on the radio or if the attacker is sitting on the host itself. But we can also do the same on the host. So we can assume that there's a malicious Bluetooth controller and then trigger issues on the host, either in the kernel or in the user space daemon, which is usually privileged. Or we can go from the other end, from the application side, where we try to inject new information from that end. So this is an interesting opportunity to test the security primitives and the security status of this complex system by breaking it into parts. And again, you see that we can only handle complexity by actually looking at the individual parts, breaking the complexity into components, and then picking these components apart to figure out what the different issues are. So to summarize the discussion about implementation complexity and implementation attacks, there's different opportunities here that enable us to analyze these large pieces of software and to pick them apart. On one hand, we can use it for binary patching and experimentation, but also to figure out more information about, for example, custom protocols, or to discover issues along the different layers of the stack. And in the end, it's software that is running on these systems, so there's bugs everywhere that we have to fix and find. It will be interesting to see how these bugs are then actually fixed and moved forward so they can be patched going forward. I've now talked about both protocol-based attacks and implementation-based attacks. Let's look forward and let's see how we can actually shed complexity and move towards a more secure form of Bluetooth. Not all hope is lost. We can break the defense mechanisms and mitigations into different parts and actually see how we can protect at all these individual steps. I want to start with an out-of-the-box approach, how we can actually shed complexity and push towards more secure Bluetooth. And this is Blue Shield, which was at the RAID this year. And Blue Shield allows us to detect attacks against legacy devices. So sometimes it will be impossible or infeasible to update the underlying devices. Now, the idea here is that we use the protocol level characteristics of these legacy devices to detect anomalies. I'm sure many of you are aware of the many years of intrusion detection systems, which were all the rage in the early 2000s in security. And it's a similar idea here. We are living in a non-perfect world, but we can extract characteristics from these devices. And especially as radio is a messy layer, we can use differences between the different communication channels and advertisement channels that Bluetooth Low Energy, for example, uses to fingerprint individual benign devices and to then detect violations at these layers of abstractions. So this is not a panacea. Like if you have the choice, we would not be using this, but this is a reasonable approach to detect violations, for example, in space or time of attacker devices against a certain usage device. Right? So this is one approach that we can do if we cannot modify the underlying behavior. We analyze the different advertisement channels. We identify the parameters of communication that these devices have as part of a profiling phase. And then during the monitoring phase, we detect if there's any additional information that, that goes beyond what we expect it to be. If we detect an illegal signal, we can raise an alarm and at least notify the users based on this issue that we discovered. So for legacy devices, this is likely the best that we can do, but can we do better? And one approach is that we've been looking at is light blue, right? I've shown you the picture about the Bluetooth stack before, and the Bluetooth stack is massively complicated. In Bluetooth, the complexity is broken up into different Bluetooth profiles. For example, a serial profile, an audio profile, human-computer interaction profile, like I/O profiles, and so on. What we do is that, or what we discovered is that when we looked at all the different devices out there, the majority of devices only use very few profiles. And these few profiles are usually not the profiles that actually have the vulnerabilities in them. So what we've focused on is to deep load and remove any of the profiles and code and functionality that is tied to these profiles from the underlying system. So we run a two-sided analysis, both on the host code, on the daemon itself, and on the firmware, to remove any of the Bluetooth profiles that are actually necessary. So on the host side, we recompile the software and remove any code associated with profiles we don't need. On the firmware side, on the controller side, we analyze the firmware and patch out and remove anything that is not required. And this then enables us to shed all the code both on the controller side and on the host side, limiting the functionality to what is actually needed and nothing else. So any bugs in profiles that would not be required for the core functionality will no longer be available, and thereby getting rid of all these different potential issues. That's not all, right? I want to highlight again the massive amount of complexity that we have here. The Bluetooth radio, baseband, and link layer, they're all pretty standard. But somebody went way overboard when designing all the different high-level profiles on top of the host controller interface. So what we've been starting to do is to get rid of all these additional layers and limit Bluetooth to an actual secure connection profile, so that you can have secure connections between two trusted parties after initial authentication and pairing, but no longer allow all these high-level protocols. In the end, we do have applications for that, an application layer of protocols. It's not the underlying communication protocol that needs to provide all this rich functionality. In the end, the applications are designed to provide these functionalities, and it's enough if Bluetooth provides a secure connection platform. So that's an interesting angle to look at that may also be interesting for some of the students in the room. The last project I would like to mention, or the last area I would like to mention to move forward, is it's pretty much an open and unsolved area, right? I've now talked to you both about protocol level vulnerabilities and implementation level vulnerabilities, and different ways how we can patch against those. And we are in this large complexity world, any software stack that we have will have bugs. So we have to come up with a way how we can actually roll out updates to all of these devices. And there's a lot of challenges involved here. For example, many of the devices will only be connected very rarely. How do you verify patches? How do you make sure that you can actually apply these patches on the system in a limited environment? How can you update the controller beyond the limited amount of patch slots that they have? For the host, look at your Android phones. When was the last security update that your Android phone received? Or iOS phones, right? iPhones. Apple will stop updating after a while. How can we continue to provide updates to all of these devices that remain vulnerable, but are no longer supported by the underlying vendors? How can we supply the patches to these systems? And how can we make sure that we can get rid of a lot of the complexity that is actually in there, right? So there's a lot of interesting issues and opportunities that we have around secure updates. And that's definitely an interesting area that we should look at more. So in the end, we want to focus on shedding complexity. And by getting rid of all of this unnecessary complexity in the Bluetooth stack, we can increase the underlying Bluetooth security. At least what we can do is we can detect attacks against legacy devices, but ideally we would do much more. We get rid of all of the unnecessary code by, for example, looking at individual profiles. But ideally, we would reduce Bluetooth to a simple communication channel. But even if it is just a communication channel, we may still wonder, how can we go beyond that? How can we provide continuous updates and patches to these devices so we can secure them against any form of attack? Let me wrap up and conclude. First off, I want to give a shout out to all the mischief makers, collaborators that worked on all of this work that I presented. First off, there's a lot of groups that already worked on Bluetooth security. I've given some pointers from other groups as well, but also in the years before, there were other groups that worked on Bluetooth security, and you should totally check them out. There's a lot of interesting pointers in the papers that I referenced in these slides. My collaborators are both at EPFL and Purdue University, and I want to give a special shout out to Daniele Antonioli, who's been working on a lot of the protocol security attacks, but also the faculty collaborators, Dave, Antonio, Dongyan, Casper, and Niels at different other places that helped me understand a lot of the subtleties of the Bluetooth standards, as well as the students working on these different issues, Xianling and Yu Hong, and Royo, and the other postdocs like Vireshwar. Right? Without their hard work and their determination to find these issues, all of this work would not have been possible. I would also like the sponsors that graciously sponsored all of this research, like the ERC, ONR, the SNF, NSF, Air Force, DARPA, and Huawei, and several others. So without the support from the sponsors, this research would also not have been possible. If you liked what I talked about, you can join the Hex Hive. The Hex Hive, I'm hiring in my research group. We are a fun group of people that are interested in working on challenging security problems. Here you see us at the CCC Chaos Communication Congress last year, where the CTF team was hacking towards flags, but we also have game consoles and a lab and other fun environments. So the Hex Hive is hiring. If you're interested in internships, PhDs, postdocs, or as faculty to visit for a semester, there's a lot of opportunities out there to join and do fun stuff on Bluetooth security, protocol security, but also other areas of system security and software security. We're an open and inclusive group, and we're looking always for fun collaborations. So let me end with the key takeaways again. This closes the loop to the beginning on how I started. Bluetooth is pretty much a mess. The protocol is extremely complex, is extremely difficult. The protocol itself is too complex, which results in protocol level bugs. The implementation is way too complex as well, resulting in implementation bugs. We need to have an emergency meeting about all this complexity, and especially knowing that attacks target all these different layers. Standard compliant protocol attacks, broad implementation bugs, they make Bluetooth security a mess. It's not all bad though. Reducing the complexity of Bluetooth is increasing security, and finding and getting rid of all of these underlying issues is key to making these communication platforms and communication protocols more secure. I hope this gave you interesting input about all the different issues that can exist in wireless protocols. This concludes my talk. I'm happy to take your questions. Thank you very much for your attention.
Thank you, Mathias. So now we have a lot of time for questions, and there is already one in Zulip chat by Kate, who asked what would a reference implementation of Bluetooth look like? So you mentioned that there is no reference implementation.
In some other standards, there's at least a reference implementation that is provided by the special interest group that tells you how it actually is or should be implemented. Right, so for Bluetooth, the protocol is defined in prose, which then, like, while there are some test vectors, for example, for some of the crypto primitives, the details of the specification are rather sparse. So there's a lot of leeway that would enable different kinds of implementations, right? And for example, the Bluetooth controllers, they are predominantly closed source. So it's highly unlikely that you will get source code for your Bluetooth controller. And having at least an open reference implementation would allow us to test these controllers. So the key, like the key novelty of the internal Blue work, or the reason why I liked it so much, is that they extracted the underlying Bluetooth firmware and then allowed further testing of this Bluetooth firmware, right? With an open standard, we could actually verify and test this open implementation to make sure it is actually correct, and wouldn't have to implement or reverse engineer a lot of these existing parts.
Okay.
Thank you for the question.
There is a question by Victor on a Zoom chat. He says the problem relies on the devices regarding all Bluetooth low energy devices. So if there is to change the complete infrastructure, so yeah, so a way.
Right. So there's a.
You can speak up, Victor.
Yeah, it's an interesting opportunity, right? Bluetooth is available in billions of devices. So billions of devices already speak legacy Bluetooth. And this huge environment has a lot of momentum to some extent, right? There's devices out there that will rarely be updated. So it would be somewhat hard to completely modify the protocol and replace it with something else. Also, on the controller side, one of the key limitations is that many of the controller implementations are implemented in ROM. So the amount of modifications that you can do on these devices is very limited. So in the end, you can only modify small parts of this implementation, maybe to patch one particular bug, but it's very hard to go beyond that. Bluetooth will likely be here to stay. The question is how we can modify parts of the Bluetooth stack to make it more secure and to make it safer.
Would there any way to rewrite the specification in 300 pages instead of 3,000?
Oh, I would hope so. This is, yeah. I would really hope so. It's I think Bluetooth is a prime example for a consortium of many companies that all like to add different features, and then you end up with something that is way over-engineered and way too complex for any practical use. So back at ETH in my undergrad, I implemented a Bluetooth stack for embedded devices based on the Bluetooth specification. And let me just tell you, it was a horrible experience to read through all of these different parts and even to get it to connect. But simple connections are not that difficult. Doing additional stuff on top of it, as exchanging audio and so on, then opens up a whole new area of difficulties that makes this ever more complex.
Okay.
I would hope that, to answer Kate's second question quickly, yes, I would hope that there would be a standard that would be better. So for example, for Bluetooth low energy, there's Zigbee, right, which is a much simpler protocol.
Yes. And so there is a question by Kate who asks, how is the Bluetooth consortium different from other standards body like IEEE?
That's a good question. So I'm not part of the Bluetooth SIG, the special interest group. I only followed some of the discussions. So this is my personal opinion and an outsider's perspective, and by no means an insider perspective. Part of it is I don't think it's different from other standard bodies like IEEE. Many of these standards have the difficulty that there's a lot of good intentions. And if you're purely focused on functionality, it's always easy to add more functionality on top. So should we add an additional protocol for an additional profile for heart rate monitors? Sure, why not? It could be useful somewhere down the line. But from a security perspective, you should be much more prudent and think about, does it actually require a heart rate monitor profile as part of the core specification? No, likely not. So maybe the security review didn't happen in line. Maybe the security people were asked too late, or I don't know, the functionality people just won over the security people. So I wasn't part of the actual discussions, but this can likely happen in any standard body when it goes out of range. The issue with Bluetooth is that we have billions of devices out there that will not be updated anymore.
Okay, thank you very much. And so, since there are lots of security problems, would you recommend to have people turn off Bluetooth on their smartphone when they don't need it?
That's a good question. It depends what the functionality you use it for. So a lot of people have gotten used to the convenience of Bluetooth. So if I look among my students, at least 80% are wearing some form of Bluetooth headsets. About 3/4 of the people have some form of smartwatch or heart rate monitor. So Bluetooth is required for the functionality of these devices. If you're considering a smart home environment, where interestingly, a lot of tech enthusiasts have smart homes, very few security people have smart homes. Right? But if you look at smart homes, all of these devices are controlled through Bluetooth. So you need to have it enabled to even have basic functionality with these devices. Now, for more recent devices on a smartphone, if your smartphone is from the last couple of years, any bug that is being found is usually patched quickly. So in all of the different issues with the Bluetooth protocols that we found, usually the vendors like Google or others were fairly responsive, and fairly responsive under a little bit of quotation marks, because it still takes a while for them to roll out patches, but they're usually responsive at pushing out patches to these systems. So I wouldn't necessarily disable Bluetooth whenever, if you have a good compelling use case, but be prudent to install any updates that are out there. That's a good question. Thank you.
Thank you. Any other question?
I see Victor had another question.
Oh, yes.
Different. Go ahead.
Go ahead.
Different Bluetooth versions are introduced every year through the problem increases with every versions. What are your views? Tough question. So the cross-transfer key derivation was only introduced recently, and the Bluetooth attacker model doesn't include any discussion of these cross-transport layer issues, which is very weird and very odd. So some of this seems like as if they didn't do enough review of the underlying specification. And I'm okay with the Bluetooth standard evolving. I would be strongly in favor if the Bluetooth standard would shed some of its complexity. And I hope with the recent flurry of all of these protocol-specific attacks that are out there, that the Bluetooth SIG, the special interest group, will take this as an input that there is too much complexity on the Bluetooth side, and that they should remove some of this complexity. They could deprecate a lot of the profiles. I think like nobody in their right minds would use 64 kilobit uncompressed audio channels anymore. But these SCO audio channels are still part of the core Bluetooth specification. So it could be a good approach to just deprecate this complexity and get rid of a lot of these unnecessary profiles. Introduce safe and secure communication channel, get rid of a lot of the complexity. That would be my way forward with the Bluetooth protocol. But again, I'm not part of the standard body. I'm just giving my outside view of this. And I'm sure there's a lot of different complexities involved internally.
Okay. So the question by Christophe on the cryptographic level. Are the cryptographic primitives specified? If so, do they have some provable security properties?
Cryptographic primitives are specified. Yes, we also did a formal analysis of the BLE reconnection. So you can look at our Wood paper from this year, which actually won the Best Paper Award, where we looked at some properties in for Bluetooth Low Energy. There's a lot of opportunity to check out additional parts, though. Right, we're only scratching the surface. From my perspective, it looks as if the standard so far neglected attackers that have capabilities to send arbitrary messages on the wireless medium, because a lot of the protocol and negotiation is happens in clear text during the setup phase. So that's definitely an area that would benefit from additional rigor and analysis among those parts, especially on the formal analysis. So if you're into this, please go ahead, be my guest, and find more issues. It's always great to have more people looking at these parts, and there's a lot of complexity in the specification to look at. Thank you for all these questions. They were great. I remain available. Reach out to me on Twitter, by email. Just sync out, give out a shout. Happy to answer more questions.
Okay, so thank you very much for your talk and the lively discussions that we had. And thank you for all for listening.